Now, not only is this part of the circuit reducible, but the entire circuit is reducible. So I already decided that these were 6 kiloohms. Now if I combine these, I can get this voltage, let me call that V sub x, out of a voltage divider. So I can do two resistance combinations and a voltage divider. I've already seen that with nodal analysis I have basically two equations and two unknowns. If I do mesh analysis, I'll end up with two mesh loops, I1 and I2. So I'd have to solve for two equations and two unknowns, and then V0 would be 2 kiloohms times I2. That seems like kind of a lot of work, so I think the approach I would take with this circuit is to entirely do circuit reduction. So we've already seen that this circuit reduces to 6 volts, 2 kiloohms, 2 kiloohms. Those two were in series, they combine to 6 kiloohms. These two are in parallel, so that becomes 2 times 6 over 2 plus 6 kiloohms, which is 12 over 8 kiloohms, which is 3/2 of a kiloohm. So now the circuit becomes 6 volts, 2 kiloohms, 1.5 kiloohms. This is what I called V sub x up here. So this V sub x here just becomes this V sub x down there. So V sub x is the result of a voltage divider. So that's 6 volts times 1.5 kiloohms over 2 kiloohms plus 1.5 kiloohms. Then once I know V sub x, the same way I did before, this 4 kiloohm and this 2 kiloohm combination over here have a known voltage across them, V sub x. So V0 is the result of a second voltage divider, so V0 is equal to V sub x times 2 kiloohms over 2 kiloohms plus 4 kiloohms. And that is two equations and two unknowns for which I can solve V0.